prerequisites for studying the subject hydraulics and hydraulic machinery, followed by what are the basic outcomes of this subject along with the objectives. And then we have seen various topics which have been divided into 5 units in the last class. Like open channel hydraulics is one part basically we study in the first unit. And in the second unit, I will be studying the dimensional analysis and more dimensional analysis techniques and model investigation. Third unit, basics of turbo machines. Fourth unit, about the hydraulic turbines principles. And then fifth unit, about the centrifugal pumps. So these are the 5 units which we would be dealing in this subject, hydraulics and hydraulic machinery. So we are now taking up the topic open channel flow with a brief introduction, and we try to see what is this open channel flow. How is it different from pipe flows? Because pipe flow already you are well versed. You have studied in fluid mechanics subject. How is it different from a pipe flow, and what are the various types of flows in open channels, and how do we classify the open channels, and how the velocity gets distributed in the open channel? And because of this non-uniform velocity distribution across a section, how to implement the correction factors like kinetic energy correction factor and momentum correction factor for getting the actual kinetic energy and for getting the actual momentum flux. So this is what we try to discuss in today's class. To give a brief introduction about the open channel, we have studied pipe flow. So a pipe is maybe a closed conduit, and the flow takes place in the pipe under pressure. How is it different from the open channel? Please note that both are the conveying systems. Pipe also carries the fluid from one place to the other place. The channel also carries the fluid from one place to the other place. But there is a difference in the process of conveying this liquid from one place to the other place. Open channel is a conduit in which liquid flows with a free surface. In the case of contrary to this, if you take a pipe flow, entire cross-sectional area of the pipe is completely filled with the flowing liquid in the case of pipe flow. Whereas in the case of open channel flow, you have a free surface. In the figure, you can see what is this free surface. So this is a canal carrying water. So for this, the top water surface is called the free surface. The top water surface is called the free surface. Over this top water surface, you have atmospheric pressure. And beneath this top water surface, the liquid which is being carried is available. So the interface between these two is called the free surface. So you have a free surface in the case of a canal flow or an open channel flow. Whereas in the case of pipe flow, the entire cross-section area is completely filled with the flowing liquid. So the free surface is actually an interface between the moving liquid and the overlying fluid. A small cross-section is shown here for this canal. For the same canal, a cross-section is shown here. So maybe a trapezoidal section. So for this, you must have noticed that all this blue portion is the one through which the water is carried. And above this is atmospheric pressure. So this line is called the free surface, which is an interface between the overlying atmosphere and underlying flowing fluid. So the free surface is actually an interface between the moving liquid and the overlying fluid. Overlying fluid is atmosphere in this case. Okay. In civil engineering applications, water is the most common liquid with air at atmospheric pressure as the overlying fluid. So you have the atmospheric pressure here, and you have the flowing liquid, which is water. Mostly in civil engineering applications, where you have the flow of water in a stream, flow of water in a river, flow of water in a canal, wherever you take, we deal with the water which is with a free surface having that the interface and over which the overlying fluid is atmosphere. This is a very common application in civil engineering. So it need not necessarily be a trapezoidal section. Canals may be, or channels may be of any shape. So different shapes are shown here, like a rectangular canal, or a trapezoidal canal, or maybe a triangular canal, maybe circular, parabolic. Several shapes of the canals could be there. But in the figure, just to have a typical representation, a trapezoidal canal is shown here. Cross section of a trapezoidal canal is shown here. So what is to be understood here is, I've been using two terms now. Sometimes I'm using canal, sometimes I'm using channel. So you should understand what is the difference between these two and how they can be the synonyms from one to the other. This also is very, very important. So in the figure, what is that you are observing? It is a canal. I say that it is a channel, open channel. How is it? How is it? This is one canal carrying water. This is also a canal carrying water. So what is the difference between this channel and a canal? Canal may be for a specific purpose, like carrying water for power generation, carrying water for domestic needs, for carrying water for irrigation. Like that, maybe a canal may be there is specific, whereas channel is a generic term. That means you have a free surface. Wherever you have a free surface, it is called a channel. It is called open channel. Well, the moment I say free surface, you have underlying flowing liquid and overlying atmosphere. If this condition is satisfied, we say that it is channel. Need not necessarily be a canal. But if you take a river, so can you just imagine how the river flows? The water in the river flows from higher energy levels to lower energy levels, and there will be a top water level, which is called the free surface, below which the flowing liquid water will be there, and above that there is atmosphere. There is atmospheric pressure. So a river also becomes an open channel. So this is the difference between a channel and a canal. Open channel may be a canal, maybe a river, maybe a stream, maybe a drainage conduit. Anything can be there in open channel. But specifically canal, if we say, a canal may be carrying water for a specific purpose. So this is how the difference. But loosely, we may be using in place of channel, canal, in place of canal, channel sometimes. But strictly speaking, there is a difference between open channel and a canal. So canal may be carrying water with a free surface, but for a specific purpose, whereas open channel could be a river, open channel could be a stream, open channel could be a canal, open channel could be a drainage also. Okay, so that is how the terms like open channel and canal. Okay, so the shape of the canal may be different, as we have been discussing, like a rectangular canal may be there, or a trapezoidal canal may be there, or a triangular, or parabolic, or semicircular, or circular. So several shapes would be there with specific purposes. Okay, so if you look at the longitudinal section of a trapezoidal channel, if you see here, you can notice that there is an arrow here which indicates this is the top water surface. So this top water surface is called the free surface, and if you see the cross section is a trapezoidal channel section. So the moment I say it is a trapezoidal channel section, there will be some slope to the sides, which is called the side slope. Maybe some z horizontal to one vertical. Side slopes will be there for both these sides. Apart from that, there will be a slope to the bed of the canal also, what is called longitudinal slope or bed slope of the canal. Bed slope of the canal, side slope, bed slope. There is a difference between these two. Please try to understand. If you look at a trapezoidal channel or a trapezoidal canal, there will be side slope for it. The side slope is something like this is the bed of the canal, and you have one side and the other side, and the sides may be having certain slope like z horizontal to one vertical. Could be same for both sides, could be different for both the sides also. So that is a trapezoidal channel. Apart from that, the side slope, for any canal, for any channel, even river, stream, whatever you take, there will be slope provided in the longitudinal direction of the channel. This is what is called the longitudinal slope or bed slope. This bed slope is necessary to have the flow in the canal. To have the flow, from higher energy level to the lower energy level, this longitudinal slope would be provided. Thereby, the water in the canal flows by the action of gravity. So, flow of water takes place with a free surface, and the prime motivating force for this open channel flow is that due to gravity. By the action of gravity, the water flows. How this water is flowing? By providing a longitudinal slope, bed slope to the canal in the flow direction, the water flows. So a channel may be defined as a passage through which the water flows under atmospheric pressure. In the case of a pipe flow, the water flows under pressure different from the atmospheric pressure, whereas in the case of an open channel flow, the water flows under atmospheric pressure. So a free surface will be provided. The free surface exists, and the free surface is subjected to the atmospheric pressure in the open channel. Let us try to compare this open channel flow with the one which we have already studied, pipe flow. We try to compare both. So what is this pipe flow? So in the case of a pipe flow, for the entire cross-sectional area of the pipe, the liquid is occupied. So the water flows, the liquid flows under pressure in the case of a pipe. Whereas in the case of open channel flow, there is overlying atmospheric pressure, and by creating longitudinal slope or bed slope, the water flows from one level to the other, from one section to the other section. So there will be a free surface. This is one basic difference between the open channel flow and a pipe flow. In the case of pipe flow, you don't have any free surface. You don't have any free surface. In the case of a closed conduit or a pipe flow, the entire cross-sectional area is completely filled with the flowing liquid, and the liquid flows under pressure. But in the case of open channel flow, the water flows by the action of gravity. The water flows by the action of gravity with the free surface or the overlying, the interface with the interface between the overlying atmosphere and underlying flowing liquid. So just look at the velocity distribution. For the case of a pipe flow, you must already studied that there will be a parabolic or a logarithmic velocity distribution with minimum or zero velocity at the pipe boundary, and as the distance from the boundary is increasing, the velocity also increases, reaches the maximum value of the velocity at the farthest point from the boundary. At the farthest point from the boundary. Obviously, for a pipe cross section, the farthest point from the boundary would be the center. So at the center, the velocity is the maximum. Whereas at the pipe boundaries, following the no-slip condition, the velocity could be zero. The velocity could be zero. So this is the velocity distribution in the case of a pipe flow. But for open channel flow, it could be different because you don't have a complete boundary. You don't have a complete boundary because there is a free surface. In the case of pipe flow, there is no free surface, whereas in the case of an open channel flow, there is free surface. So this is how there is a difference between the open channel and pipe flows. So in the pipe flow, the flow is under pressure, which can be known by inserting a piezometer. What is a piezometer? It's a small device which can be used for the measurement of the pressure, like a glass tube connected with a scale. You must have seen. You must have studied in your fluid mechanics subject, like piezometer is a pressure measuring device, U-tube manometer, differential manometer, all these are the pressure measuring devices. So piezometer is a simple glass tube arrangement connected with a scale. So wherever you would like to measure the pressure of the flowing liquid, insert the piezometer corresponding to the pressure of the flowing liquid in the pipe. There will be a rise of liquid in the glass tube. Since the glass tube is already fitted with a scale, you will be able to know how much is the rise of liquid in the tube. And the top of this tube, the other end of the tube of this glass tube is open to atmosphere. So corresponding to the pressure of the flowing liquid in the pipe, there will be rise of liquid. Accordingly, by fitting this with the scale, you'll be able to measure how much is the pressure. So in the pipe flow, the flow is under pressure, and which can be known, which can be measured by inserting a piezometer. If you insert several piezometers at different locations all along the pipe, the line joining all these points will give you hydraulic grade line, HGL, which you have studied in fluid mechanics. HGL, hydraulic grade line. It is the line joining the points of piezometric heads. How do you join all these lines? By inserting the piezometers at different locations all along the length of the pipe, and then corresponding to the pressure of the flowing liquid at that section, there will be rise of liquid in the glass tube, and the line joining all such points gives you the hydraulic grade line, HGL. The line joining the water levels in the piezometer tube installed at different sections is known as hydraulic grade line, HGL. As long as the fluid is ideal, I repeat, as long as the fluid is ideal, in all these glass tubes, you should have the liquid level at equal levels, the liquid at equal levels. Since the fluid is real, there will be resistance to the motion through these glass tubes from one point to the other point, as a result of which from one point to the other subsequent point, there will be a reduction in the liquid levels. There will be reduction in the liquid levels. So this is what is called the hydraulic grade line joining all these points. Line joining all these points. So Reynolds experiment you must have conducted. So the line joining the water levels in the piezometer tube installed at different sections is known as the hydraulic grade line. In open channel flow, now we are coming to the open channel flow. How do you get these lines if you insert a piezometer? So in the case of open channel flow, since the liquid is already under atmospheric pressure, even if you insert a piezometer at different points along the length of the river or along the length of the open channel, there will be no rise of liquid. Why there is no rise of liquid? In the case of pipe flows, corresponding to the pressure of the flowing fluid, if you insert a piezometer, there will be rise of water level or liquid level. But in the case of open channel flow, since the flow is under atmospheric pressure, there will be no rise of liquid at all. There is no rise of liquid, which means that the free surface in the open channel itself acts as the hydraulic grade line, HGL. This is another difference between the pipe flow and open channel flow. I repeat again. In the case of a pipe flow, since the liquid flows under pressure, if we insert the piezometer corresponding to the pressure of the flowing fluid, there will be rise of liquid in the glass tube, in the piezometer. Corresponding to the pressure in the pipe at that particular section, there will be rise of liquid. Other end of the tube, of course, is open to atmosphere. It is open to atmosphere. In the case of open channel flows, even if you insert the piezometers at different locations along the length of the open channel, there will be no rise of liquid in the glass tube. For a very simple reason that since open channel flows are free surface flows which are directly open to atmosphere and which are not flowing under pressure, so the free surface directly will act as the hydraulic grade line. So in open channel flow, the free surface itself acts as the hydraulic grade line. If you take a pipe flow, so this is a pipe flow laid with respect to a datum. If you apply the Bernoulli's equation between the two sections, how do you calculate the total energy? The total energy or the total head at any section would be sum of three heads: elevation head, pressure head, and velocity head. Let it be section 1, let it be section 2, anywhere. So line at a particular point, say section 1, at section 1 for this pipe flow, elevation head, jet, P by gamma, the pressure head, V square by 2G, the velocity head. Sum of all the three gives you the total head at this section. The total head at this section. Line joining all the points of these piezometric heads is called the hydraulic grade line. And if you add V square by 2G at different sections, then the line joining the total energy at all these points is called the energy grade line or total energy line. TEL. HGL, TEL. HGL is the hydraulic grade line joining the points of piezometric heads, and energy grade line or total energy line is the line joining the points of total heads. Total head, by the definition of the Bernoulli's equation, total head will have the sum of three heads: elevation head or datum head, pressure head, velocity head. Jet, P by gamma, V square by 2G. Jet, P by gamma, V square by 2G. So at this section 1, we have jet 1, plus P1 by gamma plus V1 square by 2G. Similarly, at section 2, Z2 plus P2 by gamma plus V2 square by 2G will be the total head. Provided that the fluid flowing through this pipe is ideal, the total head at section 1 must be equal to the total head at section 2. This is what we have learned in our pipe flows. This is what we have learned in our pipe flows, or application of the Bernoulli's equation. So the Bernoulli's equation says that the total head is constant along the flow. The total head is constant. That means the total head Z plus P by gamma plus V square by 2G at section 1 is equal to the total head Z plus P by gamma plus V square by 2G at section 2. Total head section 1 must be equal to the total head at section 2. This is what the Bernoulli's equation says. But there is an assumption while deriving this Bernoulli's equation. We said that the flow is ideal. The fluid is ideal. If the fluid were to be real, what would be the problem? The problem is, since the fluid is real, it possesses the property viscosity. Since there is viscosity for the fluid, which offers resistance to the motion of this fluid in the form of layers through this pipe. So from section 1 to section 2, when the fluid is reaching, there will be resistance. So to overcome this resistance, some energy would be consumed. So the total energy at section 1 is not equal to the total energy at section 2. Total energy at section 1 is not equal to the total energy at section 2. And there will be a difference of these total energies from section 1 to section 2, which is called the loss of head energy loss, HL. Okay, so if you wish to apply the Bernoulli's equation between the two sections in a pipe flow, we say that Z1 plus V1 by gamma P1 by gamma plus V1 square by 2G is equal to Z2 plus P2 by gamma plus V2 square by 2G plus HL, loss of head, HL, the loss of head. This loss of head may be constituting with major losses and minor losses. So major loss, of course, you may be knowing loss of head due to friction is the major loss, and all other losses are the minor losses, like loss at entry, loss at exit, and then loss due to sudden enlargement, loss due to sudden contraction, gradual enlargement, gradual contraction, or maybe at a bend. At all these places, the loss that is occurring is a minor loss, and of course the major loss is loss of head due to friction. Loss of head due to friction. So this is all the case which we have already studied in our pipe flow while applying the Bernoulli's equation. Now we are now trying to look at the open channel flow. We are trying to look at the open channel flow. So simple comparison is given in this figure for both open channel as well as the pipe flows. So in the case of the pipe flow, so if this is the datum line and this is the pipe, you see here how the pipe is provided with a velocity V1 and with a velocity V2 here. So the velocity here is V1, the velocity here is V2, and the line joining all the piezometric heats is called the hydraulic grade line HGL. Line joining all the points is the hydraulic grade line HGL. In the case of a pipe flow, it may be somewhere here. It may be somewhere here. But in the case of open channel flow, the depth of flow at section 1 itself will be representing the water surface. Similarly, Y2, the depth measured from the channel bed. So line joining the points Y1 and Y2 gives you the water surface, also will act as the hydraulic grade line. It also will act as the hydraulic grade line. So in the case of open channel flow, the water surface itself will act as the hydraulic grade line. And from there, if you add V square by 2G, the velocity head at different sections, the line joining all these points gives you the total energy line. TEL, the total energy line. Here also same thing. So with respect to the hydraulic grade line, if you add the velocity head at different points, line joining all these points gives you the total energy line, TEL. So it is shown here with the open channel flows and with the pipe flows, how this hydraulic grade line and how the total energy line are different. So this figure would be probably providing you a little more clarity as compared to the previous figure, where you can notice that this is the pipe flow, and with respect to the pipe flow, if you insert a piezometer, there is a rise of liquid. Similarly, another piezometer is inserted, there is a rise of liquid. Line joining these points gives you the hydraulic grade line. But in the case of open channel flow, this is the bed of the channel, bottom of the channel, or bed of the channel, and this is all the longitudinal section where there is water. So the top free surface, the top water surface, also called the free surface, is directly acting as a hydraulic grade line, HGL. Plus V square by 2G gives you the total energy line. Here also plus V square by 2G gives you the total energy line. So this is how there is a difference between the hydraulic grade line, between the open channel flow and the pipe flow. One more point I thought of telling you here. One more point is, if you apply the Bernoulli's equation, you may be getting the total head like Z1 plus P1 by gamma plus V1 square by 2G. But whereas here it is Z1 plus there is no P1 by gamma. Instead, what is there? It is the depth of water available with respect to the channel bed. So Z1 plus Y1, the depth of flow, plus V square by 2G gives you the total head at this section in a open channel flow. This is another difference between the open channel and pipe flows. In the case of a pipe flow, since the fluid is under pressure, the corresponding pressure at P1 by gamma is considered. Whereas in the case of open channel flow, since the water flows under atmospheric pressure, the depth of flow with respect to the channel bed is considered. So Z plus Y plus V square by 2G gives you the total head by applying the Bernoulli's equation in the case of open channel flows. What is Z? Z is the datum head, elevation head with respect to any arbitrary datum up to the channel bed. Why? The depth of flow at that particular section, the depth of flow means it is the actual height or the difference in level between the top water surface to the bottommost point of the channel. So this is the depth of flow Y. So Z plus Y plus V square by 2G gives you the total head in the case of open channel flow by applying the Bernoulli's equation. So this figure also would be giving you same information. And of course, I need to introduce a term like control volume. You know very well we have several approaches like control volume approach and system approach for analyzing our fluid flow problems. So we'll be adopting a control volume approach. So this is a volume which is formed between any two sections through which the flow is taking place. For example, this is a longitudinal section of a canal. Longitudinal portion of a canal. Then what we do? So this hatched portion provides you the channel bed. And if you have taken section 1 here, and if you have taken section 2 here, then the volume which is formed between the section 1 and section 2 is called the control volume. Usually, we adopt the control volume approach for analyzing these open channel flows. So to get the total energy line, as we indicated, it is the hydraulic grade line plus V square by 2G. The intercept over and above the hydraulic grade line gives you the velocity head V square by 2G. So HGL, hydraulic gradient, plus V square by 2G, the velocity head gives you the total energy TEL. Okay. There will be longitudinal slope for any of the open channels because by the action of gravity, the flow takes place. So to have the flow, longitudinal slope at the channel bottom is provided. Okay. So with this brief introduction and comparing with the pipe flow which we have already studied to this open channel flow in terms of few definitions like hydraulic grade line and total energy line, we made certain introduction. What is this open channel flow? It is something like a river flow, something like a stream flow, something like a drainage flow, something like a canal flow. In all these cases, there will be a free surface. If there is free surface, it is open channel flow. If there is no free surface, and if the entire cross section is completely filled with the flowing water, then it is pipe flow. So this is the basic difference between pipe flow, open channel flow. So open channel loosely may be used like a canal also, but strictly speaking, canal is only a subset of the open channel. Open channel can be a river, open channel can be a stream, open channel can be a drainage, open channel can be a canal, anything can be there in the open channel. How do we classify these open channels? How do we classify these open channels? In the previous figures, I have shown one open channel where the canal is trapezoidal in section. So this is one type of canal where you have All these parameters are constant along the length of the canal. You can see here, this is the cross section. Same is the cross section here, same is the cross section. So there is no change in the cross section all along the length. So such a channel is called prismatic channel. So one type of classification for the open channels is prismatic and non-prismatic channels. A channel in which the cross-sectional area, shape, size, and also the bed slope are constant is called prismatic channel. So if these things are not changing, then it is called a prismatic channel. Cross-sectional area, shape, size, and the bed slope, bottom slope. If all these are constant along the length of the canal, then it is called a prismatic channel. Like rectangular, triangular, circular, all these channels with constant parameters is called a prismatic channel. Non-prismatic channel is the one in which the cross-section area, shape, size, and also the bottom slope, bed slope are not constant, is termed as a non-prismatic channel. That means you have some shape channel here, maybe a rectangular shape channel. After certain length, maybe 1 kilometer, 2 kilometers or so, it is changed to a rectangular channel. So if we take the entire length of the canal, maybe for 4 kilometers, first 2 kilometers trapezoidal, second 2 kilometers rectangular, so it becomes non-prismatic. The slope also may be changing for various conditions, for various reasons. The longitudinal slope may be changing. So if the longitudinal slope is changing for the first 2 kilometers and then next 2 kilometers the slope is different, then it becomes a non-prismatic channel. Then what is prismatic channel? You consider only first 2 kilometers where there is no change, then that part will be a prismatic channel. If you take only second 2 kilometers where there is no change, once again it is a prismatic portion of the open channel. But part 1 and part 2 together it becomes a non-prismatic channel. So if the cross-sectional area, size, shape, and bed slope are not constant, it is termed as a non-prismatic channel. The second classification is rigid and mobile boundary channels. What is this rigid boundary? What is the mobile boundary? For a canal, for a channel, if you observe, this is what is called the side of the channel. Similarly, this is also side of the channel. And this is the bottom of the channel. So there is side, bottom, and side. This total thing constitutes boundary of this canal. The bottom and this side together, all this together constitutes the boundary of the channel. This boundary may be rigid. This boundary may be sometimes deformable also. In the figure, what is shown here is something like cement blocks are provided. Are you able to see? This is not a simple open channel. The channel completely cement blocks are provided. All this is the very regular cementing shape which is provided. Even bottom also it must have been, we are not able to see. So the boundary of this will not deform. If the water is flowing there, the velocity may be varying seasonally, hourly basis, daily basis, depending on the discharge into the canal. The velocity of the flow of water in the canal may be varying. But however, the shape of this is not changing. The shape is not changing because usually when the water is flowing, you must have seen in several videos also, particularly during the flood periods, huge water coming with high velocity possesses more and more kinetic energy, as a result of which a lot of erosion takes place. Because of this erosion, the shape of the canal at different sections would be changed. But in this case, in the figure which is shown here, this is all a very rigid surface. It is not simple at the embankment. It is a rigid surface which is provided. So irrespective of the velocity of water in the canal, the shape would not change. That means boundary is not deforming. There is no covering for this canal. There is no erosion for the sides and the bed of the canal. Such a canal is called a rigid boundary canals. The other type is the mobile boundary. So rigid channels are those in which the boundary is not deformable, in the sense that the shape, planiform, and the roughness magnitudes are not functions of the flow parameters, irrespective of the discharge, irrespective of the velocity that is taking place in the canal. The shape will not change, the cross-section area will not change, the roughness magnitudes also will not change. Such a channel is called rigid channels. On the other side, mobile boundary channel is the one where you have these parameters changing. Example for a rigid channel is lined canals. Sewer pipes means which carries the drainage water. Then non-erodible canals. So there is no erosion taking place, and channel geometry and roughness are constant with respect to the time also. Only 1 degree of freedom. The depth of flow may be changing, nothing more. The shape will not change, cross-section area will not change. Nothing will change. Such a channel is called the rigid boundary channel. We have many unlined channels in alluvium, both man-made channels and natural channels, in which the boundaries undergo deformation due to the continuous process of erosion and deposition due to flow. Please try to note what is this erosion and what is this deposition which is taking place in a canal or in a river. River also is an open channel, right? So when the water is flowing in a river, stream or a canal, there is every possibility, because it possesses more and more kinetic energy, velocity will be there. Particularly in the alluvium channels, in the alluvial channels, there is simple sand particles at the sides and bottom. Only sand particles will be there. So these sand particles will have a tendency to move up and move along with the flow of water. Along with the flow of water, the soil particles at the sides and bed of the channel will have a tendency to get lifted up and flows along with the flow of water. Where does they flow? They flow as long as the velocity is maintained. At some section, after flowing for about say 100 kilometers also, if the velocity is reduced there because of the longitudinal slope constraints, if the velocity is reduced, slowly these soil particles will have a tendency to settle down. So the place where the soil particle is removed from the section, it is called erosion. Where the soil particle is getting deposited, settling there is called the deposition. Erosion and deposition is a very common phenomenon in the rivers or streams. That is what is called silting. You must have seen, you must have observed that in some of the rivers, silting takes place very quickly because so much of soil particles will be coming. You have constructed a reservoir by constructing a dam across the river. So all the water gets accumulated in the reservoir. Since the water is getting accumulated there, the velocity will be brought down to zero. Since it is getting to zero velocity, the soil particles which are carried along with the flow of water settles down. Deposition takes place. This is what is called silting. Sometimes, the reservoirs will be fully silted up and become useless also. You have a dam constructed by investing thousands of crores of rupees, but later, after some time, the dam becomes of no use. The reservoir cannot be used for anything because of more and more deposition or silting which is taking place. Of course, several methods are there to remove this silt or to allow the silt to flow through the sluice gates to the downstream portion to see that the reservoir is becoming more and more effective for longer duration of years. So, as far as the present context is concerned, a rigid boundary, mobile boundary. Rigid boundary is the one in which the sides and bed of the canal, which are known as the boundaries, are very constant with respect to the flow parameters. If they are changing, then we say that it is a mobile boundary channel. The boundary of the channel is mobile. In such cases, the flow carries considerable amounts of sediment, silt through suspension and in contact with the bed. So in such case, there will be 4 degrees of freedom. Depth of flow may be changing, bed width also will change because after some time, the shape will be changing. Planiform may be changing, longitudinal changes. Everything, the layout will be changing. You can observe in this figure, this is a simple rectangular channel which is provided with a very rigid surface. Since the sides and bed of the surface are very rigid, there will be no change in the planiform. There is no change in the channel geometry. It is called a rigid boundary channel. On the other side, mobile boundary, you can see in the figure, as the flow is taking place, the shape also is getting changed. You can see here, the width here may be more, the width here may become less also. Okay, so because more erosion, less erosion, deposition, these are the things which are affecting the mobile boundary channel. So the second classification is rigid boundary, mobile boundary channels. The first classification of the open channels that we have seen is prismatic channel, non-prismatic channel. Third classification is natural and artificial channels. A natural channel is the one which has irregular section of varying shape, which is developed in a very natural way. How the streams and rivers are developed? Just by having a flow from high level to low level, higher energy level to lower energy levels. So if you take a cross section of such type of rivers or streams, there is no specific regular shape. So the shape may be something like this. So this is the irregular shape. So this type of irregular shape may be there for all the natural channels because they are formed in a natural way. They are not man-made channels. So flow in a river is the best example for a natural channel. Flow in a stream, the one which is built artificially for carrying water for various purposes, maybe for irrigation, maybe for power generation, maybe for domestic water supply. When you are preparing, naturally the channel will be with a very specific shape. You see here, the shape is so specific. So these are called the artificial channels where you have very specific shapes. Usually the artificial channels will be with a very clear-cut shape of rectangular, trapezoidal, something like that, triangular, and so on. Okay. Then see the natural channels how they're formed in way because of huge rainfall in the hilly area. It is getting collected, trying to flow to the downstream portions or to the lower energy levels. So naturally, this is a natural stream. So there is no specific shape for it. So these are all called natural channels. All rivers belong to the class of natural channels. Okay. Fourth classification is based on the regular geometrical shapes. So you have geometrical shape like rectangular. See this canal. How is this? A rectangular channel. A rectangular channel, of course, maybe for power generation, maybe for agricultural purpose, like irrigation. The channel is laid alongside, and you have a very specific rectangular shape. Okay, so you have these geometric shapes like rectangular, trapezoidal, triangular, circular, parabolic, several shapes are there. Okay, elliptical, egg-shaped, egg-elliptical shape, several shapes of channels. Why do we require several shapes of channels? To see that these channel sections are more and more efficient. Sometimes, at a particular location for a specific purpose, rectangular channel may be giving best hydraulic efficiency. So it is a hydraulically efficient channel. But some other location, egg-shaped channel may be giving good. So when you see the efficiency with respect to the hydraulic parameters, the channel shapes would be changing. Like rectangular, trapezoidal, triangular, circular, parabolic, elliptical, egg-shaped, egg-elliptical shape, horseshoe shape, like that. Several shaped channels will be there. Of course, the specific design for each shape would be different. A small study also has been carried out by one of my researcher, which shape would be useful where, and so on. So he also tried to develop a few shapes, horseshoe shape, and then he tried to evaluate the parameters relating to those shapes also. The fifth classification is about the open and closed channels. The channels having cover at the top are known as closed channels. You see here the difference between a pipe and a closed channel. In the case of pipe, entire cross section is completely filled. But here in a closed channel, the cross section is not completely filled. However, the top is covered. You see this shape, rectangular. The top also is covered here. The water is only up to this level. Water is only up to this level. But in this case, the top is not covered. The top is not covered. Okay, so this is not covered, and whereas this is a covered channel. So this is called the closed channel. So in this circular section also, the water is only up to free surface level. So there is a free surface, and hence this becomes an open channel. It becomes an open channel flow. Pipe flow different from open channel flow. In the case of a pipe flow, entire cross section is completely filled with water. There is no free surface. But for the same pipe, if the water is flowing partially full, that means only up to this level. So over this, the pressure becomes atmosphere, and hence this pipe also becomes an open channel. The pipe becomes open channel if it is not running full. If the cross section is not completely filled with the flowing liquid, a pipe flow becomes an open channel flow because there will be a free surface, there will be water surface. Okay, so usually these closure channels, that means the top is covered in particularly when you have underground drainage system, then or sometimes tunnels which are provided. So in such case, we try to provide the tops which are covered, particularly in the urban scenario also, the drainage cannot be left open to atmosphere. Instead, all the drains will be covered. If the drain is completely covered, the top space may be used for parking, sometimes may be used for footpath, etc. Okay, so we have seen basically about 4 types of channels, 4 types of channel classifications. Prismatic and non-prismatic channel is one category, rigid boundary and mobile boundary channels, natural and artificial channels, and depending on the geometric shapes, and finally the covered and uncovered or closed and open channels. Okay, a small video I'll be able to play. Let me just see.
Compared to the great rivers of the world, the water of Leith here in Edinburgh is a tiny stream, but we can still see lots of evidence as to how important it's.
Is it audible and visible?
Yes, sir.
Okay.
Been to society over the years. The weir behind me here was built to raise the water level so that it could be used to drive water wheels that powered the industry that was formerly located in the Dean village here. Nowadays, this particular stretch of water is an important amenity, with the pathway providing a safe route to walk or cycle to work. Engineers have had to ensure that, as development proceeds on either side, the riverbanks are protected against floods that occur with increasing frequency. Let's look at the way the water negotiates obstacles such as the weir here. The very crest of the weir is a free overfall. There's no resistance to the flow on the downstream side. So as soon as the water has the very minimum of energy it needs to pass the weir, it plunges over in the torrent that you see behind me. We can see this more clearly in the laboratory. Here we see water building up behind a model of a weir. The water has been coloured for visibility. As soon as it has enough energy, the water spills over the weir. The depth of water over the weir is called critical depth, and this depth is constant for a given flow rate and weir geometry. The water behind the weir is deep and slow flowing, a form of flow known as subcritical flow. At the edge of the weir, it spills over and falls rapidly to the channel below. From the engineering point of view, what is really interesting is the shallow, fast flow on the downstream side of the weir. Here we see water with lots of kinetic energy, which could do a great deal of damage downstream if it were not handled safely. This kind of flow, the flow we get downstream of weirs and at various points in rapids in natural rivers, is called supercritical flow. This is often something that engineers need to control. If the depth and flow conditions downstream are correct, the flow can be forced to return to a slower, deeper subcritical regime by means of a hydraulic jump. A hydraulic jump is a standing wave, typified by quite violent eddies and white water. Here we can see the supercritical flow and the hydraulic jump that forms naturally around rocks in the river. This overhead view shows the hydraulic jump running across the centre of the screen, with supercritical flow clearly visible above it. We can see the hydraulic jump again in the laboratory flume. Flow spills over the weir and becomes supercritical, but downstream the flow is restricted and a jump forms, forcing the water back to a subcritical regime. The view from the side is much more striking. Flow over the weir and the shallow, fast supercritical flow contrast with the deeper subcritical flow downstream of the hydraulic jump. Jump itself takes the form of a jet of water close to the bed, with eddies peeling back off it to form the white water on the surface. In the field, the details are not so clear, but the basic form of the jump can still be made out. The formation and location of a hydraulic jump depend on the downstream conditions. In the laboratory, we use this adjustable sluice gauge to restrict the flow out of the flume, forcing the flow to become subcritical again. We can see the hydraulic jump gradually creeping up the flume until it stabilizes right against the weir. Finally, opening the sluice removes the restriction on the flow, allowing supercritical flow to continue down the flume and causing the hydraulic jump to be washed out completely.
Okay, so in this video, you have seen about a simple natural channel to an artificial man-made canals, followed by how the experimentation is taking place for different types of flows in the laboratory, as has been shown. But that part, of course, is not very comfortable for us now, because the hydraulic jump, those parameters we have not yet introduced it to you. But what I would like to tell you is that, so it is all natural phenomena in a river, in a stream, the water flows. So you will not be able to ascertain the specific shape there. Also, the shape would be changing from one point to the other point, from one section to the other section, depending on so many parameters, not only the simple flow. Second thing is that when the flow is taking place based on the velocity there and based on the silt or soil conditions there, the bed and the sides of the channel also may get eroded. Erosion may take place. So some portion may be a rigid boundary, some portion may be a mobile boundary, some portion may be a very artificial, some portion may be completely purely natural. So all these combinations would be there when you are having a stream or a river or a canal. Okay. Now we take up the next topic about the classification of flows. How do we classify the flows in the open channels? Steady and unsteady flows, uniform and non-uniform flows, laminar and turbulent flows, subcritical, critical, and supercritical flows. These flows already we have defined in fluid mechanics, like what is a steady flow, what is unsteady flow, and so on. So with respect to the open channel, what type of change would be there, we'll see here. The basic concept is same. The flow could be steady, the flow could be unsteady, depending on the variation of the parameters with respect to time. So same thing here also. But when you are talking in terms of the open channel, what are those parameters? The parameters may be the depth of flow in a canal, or maybe the velocity with which the water is flowing in the channel. These are the parameters that you need to consider. So steady and unsteady flows. A steady flow occurs when the flow properties such as depth of flow, discharge, etc. at a section do not change with respect to time. So you have a canal, and at a particular section, at 7 a.m. in the morning, you have identified that the velocity is 1 meter per second. At 7 a.m. in the morning, you identified that the velocity is 1 meter per second. At 8 a.m., once again, you measure the velocity 1 meter per second. At 12 noon, the velocity is measured to be 1 meter per second, which means that morning 7 a.m. till 12 noon, the velocity is constant, not changing with respect to time. So the flow is steady. If the velocity is not changing with respect to time, then it is called a steady flow. So the velocity, the depth of flow, these are the parameters. So flow in a channel is said to be steady if the flow characteristics at any point do not change with respect to time. So if velocity is constant, its differential with respect to time must be equal to 0. Similarly, the depth of flow is constant, its differential with respect to time must be equal to 0. So mathematically, dou v by dou t is equal to 0, dou y by dou t is equal to 0 represent the steady flows. On the other hand, unsteady flow is the one where these parameters may be changing, like velocity may be changing from 1 meter per second to 2 meters per second. So there is change of velocity. So it becomes unsteady. It becomes unsteady. So if the flow properties change with respect to time, then the flow is said to be unsteady flow. So flood flows in the rivers and rapidly varying surges in canals are some of the examples for this unsteady flow. Since the velocity is changing with respect to time, so it is not constant. So if you take a differential, dou v by dou t is not equal to 0. Similarly, its differential is not equal to 0. Dou y by dou t is not equal to 0. So this represents that the flow is unsteady, whereas this represents the flow is steady. Y, the depth of flow, V, the velocity of a flow. These are the parameters which are constant at a given point with respect to time. And then it is called steady flow. If they are not constant and varying, it is called unsteady flow. Second classification is about the uniform and non-uniform flows. If the flow properties such as depth of flow in an open channel remain constant along the length of the channel, then it is said to be uniform. It is said to be uniform. So in a river or in a canal, in a stream, if the water is flowing at different sections along the longitudinal length of the channel, at different sections, if there is no change in the depth of flow, then we say that it is uniform flow. So with respect to section, the flow parameters must be constant with respect to section. So y is constant with respect to the section. So dou y by dou s must be equal to 0. Similarly, the velocity v with respect to section is not changing. So dy by dou v by dou s must be equal to 0. Then it is called uniform flow. Otherwise, it becomes a non-uniform. A prismatic channel carrying a certain discharge with constant velocity is an example for the uniform flow. If these flow properties change along the length of the channel, the flow is said to be non-uniform, like dou y by dou is not equal to 0, dou v by dou is not equal to 0, etc. So flow in an open channel is non-uniform or varied if the depth of flow changes from section to section along the length of the channel. So you have a canal maybe of 4 kilometers. At kilometer 1, at kilometer 2, at kilometer 3, and at kilometer 4, you measured the velocity and the depth of flow at the same point of time. At a given point of time, you measured, and you found that if these are all constant at different sections, then it becomes uniform. If these are all not constant and varying, it becomes non-uniform. I hope you followed the difference between steady and steady, uniform and non-uniform. Steady and unsteady flows would be with respect to the flow parameters remain constant with respect to time, whereas the flow parameters remain constant with respect to space, with respect to section from one point to the other point. Then it is called uniform flows. So if the flow is not uniform, it is called non-uniform flow, where the depth of flow may be changing, the velocity may be changing from one section to the other section along the length of the canal. Then it is called non-uniform flow, also called varied flow, because there is variation in the depth of flow, the velocity. Then it is called varied flow. So this varied flow is further classified as a rapidly varied, gradually varied flow. GVF, gradually varied flow. RVF, rapidly varied flow. For example, in a river which is carrying flood water, the moment water is the flood water there, naturally there will be huge variation in the depth of flow as well as the velocity. Then such a flow is called non-uniform flow. So if the depth of flow changes over a long distance, it is called gradually varied. If the depth of flow is changing abruptly over a very short distance, it is called rapidly varied flow. Example for the rapidly varied flow is a hydraulic jump. Particularly, you must have seen when the gates are opened during the flood period for any of the dam structure from the reservoir, huge quantity of water, huge discharge comes out to the downstream portion, and the variation is so rapid in the depths of flows, then it is called a hydraulic jump. So example for that is the hydraulic jump. Similarly, in the upstream of a dam, the water slowly joins to the reservoir. So there is a gradual raise of water level for a long distances of 200, 300 meters, then it is called gradually varied flow. So rapidly varied flow, gradually varied flow are the parts of the non-uniform flow, also called varied flow. The third classification is about the laminar and turbulent flows. We already defined the Reynolds number in our fluid mechanics, the Reynolds number, and this Reynolds number, RE, which is the ratio of inertia force to the viscous force, is a measure for identifying the flows to be laminar or turbulent in pipes. The flow through a pipe can be a laminar flow. The flow through a pipe can be a turbulent flow. If the flow through a pipe can be laminar flow, provided the value of the Reynolds number is Re is less than 2000. If it is more than 4000, then we have stated that the flow is turbulent. Of course, in between 2000 to 4000, it is in transitional state. It is not the type of flow. Please note that it is not the type of flow. It is the transitional state where the flow may exhibit the characteristics of laminar flow sometimes. The flow may even exhibit the characteristics of turbulent flow some other times between the values of the Reynolds number between 2000 to 4000. This is all about the pipe flows. In the similar fashion, in the open channels also, laminar and turbulent flows are designated based on the numerical value of the dimensionless number, Reynolds number, which is given to be the ratio of inertia force to viscous force, rho v r by mu. Rho mass density, v is the mean velocity of flow, r is the hydraulic radius. We come back once again about the hydraulic radius shortly. And mu, that is viscosity of the flowing fluid or water here. So, based on this, numerical value of the Reynolds number Re, the flows in the open channel are classified to be laminar and turbulent flows. If the value of Re is of the order of less than 500 or 600, then it is called laminar. It is called laminar. If it is more than 2000, the flow is turbulent. This is all about the open channels. For pipe flows, it is 2000, 4000. That the story is different. Just to have a clear to have a clear recollection of what you have studied, I explained about that. So for the open channel flows, if the value of the Reynolds number is of the order of less than 5000, for 500 or 600 it is laminar, and more than 2000 it is turbulent, and in between 500 to 2000 it is a transitional state. Fourth classification is about the subcritical, critical and supercritical flows. Just like we have defined laminar and turbulent flows classified with respect to Reynolds number, one dimensionless number. Similarly, in the case of open channel flow, also another dimensionless number, which is a governing parameter, is defined. This is the Froude's number. Reynolds number there, here it is the Froude's number, which is the ratio of inertia force to force due to gravity. It is not about the viscosity. It is force due to gravity. Inertia force to gravity force. Fi by Fg is called the Froude's number Fr. This Froude's number is given by the velocity v divided by square root of g into d, where g is the acceleration due to gravity. D is another geometric property, hydraulic depth. In the earlier case, we have seen hydraulic radius. Similarly, hydraulic depth. Here I'll come back once again about that. Shortly we define. Okay, so the Froude's number Fr is equal to V by root GD, and based on the numerical value of the Froude's number, the flows in the open channels are classified. In open channel flows, gravity force is the predominant force. Accordingly, the Froude's number less than 1, subcritical, is equal to 1, the flow is said to be critical. If Fr is greater than 1, the flow is said to be supercritical flow. Just like laminar turbulent flow based on Reynolds number, we have subcritical, critical and supercritical flows in open channel flows based on another dimensionless number known as Froude's number. Froude's number is the ratio of inertia force to gravity force. If the value of Froude number is less than 1, subcritical, equal to 1, critical, and greater than 1, supercritical flow. So we have seen the types of flows in 4 categories. In first category, steady and unsteady flows. Next, uniform and non-uniform flows. Then laminar and turbulent flows. Then about the critical, subcritical and supercritical flows. So these are all the classification of flows in open channels. Now, we see about some of the geometrical properties of the channel sections. We have been using the terms like hydraulic radius and hydraulic depth and so on. Let us see what are these geometrical properties. Depth of a flow. What do you mean by this depth of flow? So in a canal, for any of the shapes, the depth of flow is from the free surface to the bottommost point. You see in the figure, this is the free surface. So from the free surface to the bottommost point of the channel is called the depth of flow. If you just leave this bottommost point, there are several points at the bed. There are several points. You may get different depths. They are not considered to be the depths of flows. Depth of flow is only one at a given section. Only one at a given section. From the free surface to the bottommost point of the channel section is called the depth of flow Y. So depth of flow Y is the vertical distance of the lowest point of the channel section from the free surface. It is measured from the free surface to the bottommost point, which is the lowest point of the channel section. Next, top width T. This top width is the width of the channel section at the free surface. So this is the free surface. For the section figure which is given here, an arbitrary shape, this is the free surface. So the width which is measured from this point to this point is called the top width T. So top width is the width of the channel section at the free surface. Then the wetted area A is the cross-sectional area of the flow section of the channel section. So what is this wetted area? So the entire cross-sectional area, if you take the cross-sectional area of the flow section, is called the wetted area. So for this, what will happen? Entire thing in the figure, all this would be the cross-sectional area of the flow. So this cross-sectional area of the flow section is called the wetted area A. Depth of flow Y, top width T, wetted area A. Then wetted perimeter. What is the wetted perimeter? It is the length of the channel boundary which is in contact with the flow of water. So this is a section that you have taken. So from this point, all this channel boundary is in contact with the flow. So length of this portion is called the wetted perimeter. It is the length of the channel boundary which is in contact with the flow. It is the length of the channel boundary which is in contact with the flowing water in any section is called wetted perimeter P. Then hydraulic radius is the ratio of wetted perimeter to, wetted area to wetted perimeter. Wetted area we have already seen. It is the cross-sectional area of the flow section A divided by the wetted perimeter is the length of the channel boundary P which is in contact with the flow. So A by P gives you hydraulic radius. This hydraulic radius R we have used in defining our Reynolds number. Rho V R by mu. This R is the hydraulic radius. Similarly, hydraulic depth D is the ratio of wetted area to top width. This is all the wetted area, cross-section area, divided by the top width T gives you the hydraulic depth. So we have defined the terms like depth of flow, top width, wetted area, wetted perimeter, hydraulic radius, and hydraulic depth. So these will be different for different sections of the channels. For different sections of the channels. For a rectangular channel, if you take, for a rectangular channel, what is the depth of flow? The depth of flow will be from the top water surface to this, so simply Y. B is the bed width of the channel section. Then what is the wetted area? For this channel section, wetted area is the cross-sectional area of the flow section. This is the definition. Cross-sectional area of the flow section. So B into Y is the wetted area. What is wetted perimeter? It is the length of the channel boundary which is in contact with the flow. In contact with the flow in this channel, if you see, starting from this point, the depth of flow Y, the bed width B, and the depth of flow Y. So Y plus B plus Y is the wetted perimeter. Is the wetted perimeter. So B plus 2Y is the wetted perimeter for this. Wetted perimeter for this. So for a rectangular channel section, A, wetted area, B into Y, P, the wetted perimeter, B plus 2Y. Hydraulic radius, of course, is the ratio of wetted area to wetted perimeter, BY, B plus 2Y. And the top width T is equal to the bed width B in this case. There is no change because it is rectangular. Because it is rectangular, the top width T is equal to the bed width B. For a trapezoidal channel, these parameters would be different. If this is the trapezoidal channel, there is a side slope. So this side slope may be z horizontal to 1 vertical. If you have, the top width and bottom width will be different. The top width and bottom width will be different. See in this figure, this is the bed width B, the bottom width, and T is the top width. So the side slope is z horizontal to 1 vertical. Then the wetted area will be equal to the cross-sectional area of the flow section. So how do you arrive at this cross-sectional area of the flow section? It is the area of the trapezoidal portion. So the central rectangular portion plus the triangular portion on either side. If we take the central rectangular portion B, bed width B, and depth of flow Y. So B into Y is the cross-section area of the central rectangular portion, followed by the triangular portion. this triangular portion. So to arrive at this portion, this component here, you have z horizontal to one vertical. For one vertical, the z horizontal portion. For y vertical, zy is the horizontal portion. So you have base of zy and depth of y, a triangle is there. So the area will be half of base into height, half into zy into y. Similarly, this side has half into zy into y. So you have half zy into y this side plus half zy into y this side. So the total cross-sectional area of the trapezoidal section would be central rectangular portion b into y plus trapezoidal portion on the left-hand side, half of zy into y. Here, this side, half of zy into y. Sum of all this will be b plus by into half zy square plus half zy square. It will become 1 zy square. Take y common. So b plus zy into y is the wetted area. Similarly, wetted perimeter is the length of the channel boundary in contact with the flow. You have z horizontal to one vertical. For this triangular portion, what would be this inclined part? Square root of z square plus 1. Similarly, square root of z square plus 1 this side. So you have the total length of the channel boundary. Total length of the channel boundary would be equal to sum of the channel bed plus this inclined portion plus this inclined portion. So y into square root of 1 plus z square, y into square root of 1 plus z square plus b. So b plus 2 by root 1 plus z square will be the total wetted perimeter. Hydraulic radius will be, of course, a by p, and the top width will be b plus 2zy. Hydraulic depth is a by t. So you have the geometric properties for the trapezoidal section. Similarly, for a triangular section, maybe you can work out for the other sections like parabolic also you can see. But mostly, we'll be limiting our study to triangular, trapezoidal, and rectangular as far as the open channel hydraulic subject is at BTech level is concerned. As we move up, probably we'll see about the other shapes also like elliptical channel, etc. Okay, so this is for the triangular channel section. Wetted area zy square, wetted perimeter 2 into root 1 plus z square, and the top width t will be equal to 2 into zy. We close at this, we stop at this point, and if you have any